Hi, everyone. Welcome to the Graphs and Matroids seminar. Today we have Daniel Slilaty talking about orientations of golden mean matroids. Daniel.
Hi, everybody. Thank you so much for having me. This is a joint work with Jacayla Robbins from Vanderbilt University. And it's a kind of a long-standing thing her and I have been working on, and finally managed to nail it down. So there's this line in research in matroid theory dealing with this notion of partial fields, and it's an idea that sort of germinated over, a good 50 years. And sort of the first inklings of it are this notion of totally unimodular matrices. So a rational matrix is totally unimodular when every non-zero subdeterminant of that matrix is +1, -1, including the 1 by 1 subdeterminants, right? So all the entries of the matrix are +1 and -1. And such a property is closed under pivoting when you're only using the +-1 scale as a scale. And it's closed under this, matrix duality type operation that's used in matroid theory and coding theory and in linear programming. So unsurprisingly, I guess this is the first usage of these total unimodular matrices was by Hoffman and Kruskal in 1956. If A is totally unimodular and B is integer vector, then the polyhedron defined by the system of inequalities AX less than or equal to B has integral vertices. So what's the upshot of that is that any linear programming problem where the set of constraints look like that, linear programming and integer programming are the same, because in linear programming, the optimal solutions are on the vertices of this polyhedron. So linear programming is, of course, computationally easier than integer programming, which is NP complete. So, I mean, it's a pretty restrictive class of matrices, but it's definitely a useful idea. All right, so a matroid is said to be regular when it has a totally unimodular matrix representation. And that's closed under taking minors and duality, because this matrix operation is closed under pivoting and duality. And regular matroids have to be binary. Why? Well, because if you take that total unimodular matrix and you look at all the entries mod 2, well, what was a 0 subdeterminant stays 0, of course, but what was a non-zero subdeterminant +or -1 stays non-zero. So that homomorphism from Q to Z2, just 1 goes to 1, -1 goes to 1, that gives you a, preserves the matrix of that matrix. Can I lower this? There we go. So in 1958, Tutt came out with this great theorem. If M is a binary matroid, then M is regular. In other words, it has a totally modular matrix representation. If and only if M is representable, F representable for some field F whose characteristic is not 2. So over Q or over GF3 or whatnot. Right. So seminal result in matroid theory. And decades later, suddenly a bunch of analogs came out for other fields rather than binary. So a rational matrix A is called dyadic when every non-zero subdeterminant is in +or -2 to the I. Again, closed under pivoting using values from this set, and closed under duality. This matrix duality, right? And then you say a matroid M is dyadic when it has some dyadic matrix representation. So So suddenly the terminology became more consistent, right? We said regular matroid, but totally unimodular matrix representation. So now the name of the matrix and the name of the matroid coincide, which is better, more easy to remember. So a matroid M is dyadic when it has a dyadic matrix representation. Again, closed under minors and duality because we're closed under pivoting and duality. And dyadic implies ternary because if you take the homomorphism from Q to Z3 by, 2 goes to 2 and -2 goes to 1, then and you apply it to a dyadic matrix, then it gives you a GF3 matrix and it preserves the matroid. So in the mid-90s, Jeff Whittle found the analog to Tutt's theorem for dyadic representation. And that is, if M is ternary matroid, then the following are equivalent. M is dyadic, M has a Q representation, or M has a GF5 representation. So this is the analog to, so maybe you can forget about 3 for the moment, but this is the analog to Tutt's theorem. And Tutt's theorem is M is regular if and only if M is F representable for some F of characteristic not 0, or M is regular if and only if it's Q representable, say. So here M is dyadic if and only if it's Q representable when M is ternary. The other was for when M is binary. And then new ideas of special matrices defined by nice subdeterminants came out. So a matroid M is near regular when it is representable by a matrix over Qx. So this is the field Q adjoined this just indeterminate element X. And representable by a matrix over Qx, where every non-zero subdeterminant is in this set, plus or minus x to the I, 1 minus x to the j. And first time I saw that, I thought, well, that's really kind of odd to define a matrix like that over a polynomial ring, polynomial field or whatnot. But, what makes it special is this theorem, really, is that if M is ternary, then the following are equivalent. M is near regular when M is GF4 and GF5 representable, if and only if M is GF4 and Q representable. So, again, showing this to be really a fundamental class of matroids representable by these types of matrices, because they're matroids that are representable over some collection of small fields. Okay. And then more of these special matrices. So let G be this golden ratio, 1 plus the square root of 5 over 2. A matrix is said to be golden mean when it has a matrix representation whose every non-zero subdeterminant is in this set, plus or minus G to the I, where I is an element of Z. So all the powers of the golden ratio. Closed under minors and duality because of pivoting. And then a golden mean matrix, this type of matrix, when you have a golden mean matrix, you can take a homomorphism to GF4 and that preserves the matroid. So you take the ring homomorphism from Z adjoined G to GF4 given by, phi of 1 is 1, of course, and phi of G is omega, where GF4 is, generated by 1 and omega. Omega is the element of GF4 for which omega squared plus omega plus 1 is 0. So Dirk Vertingen, he proved the following theorem, although he never published it. And then Rudy Pendeving and Stefan van Swam, they, in 2010, provided it's a stronger theorem that they came up with, really. But they came up with a whole new framework for all of these partial results about partial field, Tutt's result, Whittle's result, this result, and came up with more. Let M be GF4 representable. So first we started with binary, then ternary, now quaternary. So if M is a quaternary matroid, then M is golden mean, if and only if M is GF5 representable. So we've got this type of theorem for binary matroids, for ternary matroids, for quaternary matroids, and then Pendev and Van Swam, they came up with a variety of results for GF5 representable matroids. So they have a whole collection of partial fields, which they call the Hydra partial fields. And I think somebody talked about it a while ago, these Hydra partial fields, and they're a nice way of sort of partitioning the different types of GF5 representable matroids into nice, meaningful classes. All right, so a less explored line of inquiry has to do with representable binary matroids, ternary matroids, quaternary matroids, and orientations rather than representations over other fields. So let's talk about orientations. So let E be a set of elements, the set of elements of M. A signed set is a function X from E to plus minus 0, whose support is all the elements of X that are not 0. And the elements the elements of E are E, and the value of X at E, we use this subscript or notation rather than this sort of functional notation. So you've got the support, X bar, and then you've got the positive part and the negative part of every signed set. And then an orientation of M, of a matroid M. So an orientation script O of M is a collection of signed sets such that for each signed set in O, the support is a circuit of M. So instead of signed sets, now we call them signed circuits, right? So the signed sets of O are signed circuits, where X is in O if and only if, negative there, if and only if negative X is in O. X is in O if and only if negative X is in O. If X and Y are in O, and the support of Y is contained in the support of X, then Y is plus or minus X. So when we're signing the circuits, there's only two signings. There's one particular signing, and then there's its negative. There's no other signing of the same circuit. And then you've got this circuit exchange property. So it's just like the ordinary circuit exchange property, but it respects the signing. If X and Y are signed circuits and E is in the positive part of X and negative part of Y, then there is a signed circuit Z, whose positive part comes from the positive parts of X and Y, and whose negative parts comes from the negative parts of X and Y. Right, so that's just like ordinary circuit elimination. The ordinary circuit elimination axiom, except, it just respects the sign pattern in sort of the obvious way. The canonical example of an oriented matroid, a canonical example of the oriented matroid is the following. Let A be a matrix over the real numbers, and C be a circuit of MA, the matroid given by that matrix. Up to scalar multiplication, the vector X, whose support is C, and satisfies A times X equal to 0, is unique up to scalar multiplication, right? Minimal linear dependence relations on the columns of A, minimal dependence relations, the coefficients are unique up to scaling. So the sign pattern of those coefficients is unique up to negation. And those are your sign circuits. So that's the sort of motivating example, one of the motivating examples of oriented matroids. But it's not all oriented matroids. Not all oriented matroids come from real matrices. And it's sort of a big, often an important question as to which matrices come, or which orientations come from real matrices and which ones don't. The term in oriented matroid theory they often uses realizable. So how do you look at all orientations of a matroid? Well, you do them using this thing called pseudosphere arrangements in dimension R, where R is the rank of the matroid. But we don't need to, and that's the Folkman-Lawrence topological representation theorem, which I believe Laura Anderson has spoken about, but we don't need that full thing. We're just gonna need it in rank 3. So an antipodally symmetric pseudocircle arrangement is a collection of simply, what's a pseudocircle? Pseudocircle is just a circle that's got some wiggles to it. An antipodally symmetric pseudocircle arrangement is a collection of simply intersecting pseudocircles in the sphere with antipodal symmetry. So simply intersecting means every pair of pseudocircles intersects in 2 points. So no tangentially intersecting things, right? Just intersects transversely at 2 points. So here is a pseudocircle arrangement, and the antipodal symmetry allows you to do what? Take one of the circles and draw it fully. And then the rest of the circles are just lines, right? Just lines that wiggle through and end at antipodal points on the outer circle, right? So the other side of the spherical arrangement, you just take this picture, flip it around and stick it on the back, so you don't need it. But all rank 3 oriented matroids come from these things. So that's a topological object. Where is the orientation? Where are the sign circuits? It's as follows. So the pseudocircle arrangement represents a matroid of rank 3. The elements are the circles. So the elements are the lines here in the circle on the outside. So the elements are the circles, and the hyperplanes are the intersection points. So the intersection points are the hyperplanes. So this one here is Q6, right? So 1, 2, 3, and 1, 4, 5, these intersection points, that's these hyperplanes here. The 1, 2, 3 hyperplane, the 1, 4, 5 hyperplane. And then the the points that the intersection points of 2 lines are the 2-point hyperplanes, or the 2-point lines. And then what you do is you pick sides for each circle. So you got these circles, just arbitrarily pick a side. Okay, so now since the intersection points are hyperplanes, the complements of the intersection points are cocircuits, right? So this is the hyperplane 2, 3, this point right here, 2, 3. So the complement of that, no, it's 2, 4. Yeah, here it is. 3, 4. This one right here. That's 3, 4. So 3, 4, the complement of that is 1, 2, 5, 6. So we're on the positive side of 2. We're on the positive side of 1, positive side of 5, the negative side of 6. So there's the signing, plus, plus, 0, 0, plus, minus. That's the sign circuit, just picking sides. And if you want to pick the other side, if you flip the side around, all you're just going to do is negate the column. So that's the orientation of M dual. Now, once you have an orientation of the dual matroid, there's a unique way to recover the orientation of the primal matroid. We don't need to talk about it. It's by this thing, this orthogonality property. But just, once you order one of M and M dual, then you get a unique orientation of that order. Once you orient M or M dual, you get a unique orientation of the other. Here's some non-orientable matroids, and this is important for this work here. Probably you're not surprised to learn that the Fano and the non-Fano, or the dual Fano, those are non-orientable. The non-Fano is orientable. M8, this AG23 minus E, often called the MacLane matroid, that's not orientable. And of course, orientability is closed under duality, like we were just saying. So the dual of the MacLane matroid is not orientable, nor is it the the delta y exchange of the McLean matroid is that orientable either, non-orientable as well. Orientability is closed under delta y exchanges, as you might have guessed. Reorientation. So a reorientation of an orientation O on X is done by negating elements of X in each signed circuit. So that corresponds to changing sides on the pseudocircle arrangement. And in the R matrix A, you reorient A on X by negating the columns corresponding to X. So given an orientation, you can do a reorientation. Not all orientations are equivalent by reorientation. And that's the notion of equivalent orientations, whether you can reorient one orientation to get to the other. Okay, so the founders of oriented matroids were Bland and Lesvernius, and this was the first paper they wrote on the topic. And in that, they proved the following. And it's an analog of Tutt's theorem. Let M be a binary matroid. So O is an orientation of M if and only if O is induced by a total unimodular representation of M. The orientations of binary matroids come from the total unimodular matrices. And, you know, a total unimodular matrix is a real matrix, so it gives you an orientation as well. Okay, so now the question is, how many orientations can you have? Well, I mean, binary, it's known nowadays that binary matroids are uniquely representable over any field or partial field you wish to represent them over, but that all kind of started with this first result of Camus, 1963, a matroid M has at most one total unimodular representation, although he didn't really state it like that. So what about ternary? So Lee and Scobie came out with that result in 1999. Let M be a ternary matroid. O is an orientation of M if and only if O is induced by a dyadic representation. So analog of Whittle's theorem, dyadic representations come from orientation. Sorry, orientations come from dyadic representations. Dyadic representations give you orientations because, of course, dyadic representations are real. So then and I forgot to mention this one. Inequivalent. So projectively inequivalent dyadic representations give you inequivalent orientations. That's John Lee's result. John Lee was one of the first people to really study these dyadic matrices in depth. So when you have inequivalent dyadic representations, it gives you inequivalent orientations. And that basically boils down to the fact that there's 3 dyadic representations on U24, and they give you 3 orientations on U24. So now the question is, how many orientations can you have? Well, the dyadic representations are tied. The orientations are tied to the dyadic representations. So what you need to do is know how many dyadic representations you have. And Pendaven and Van Swam in 2010, this is a corollary of a more general result of theirs, but when you take it down to ternary matroids, let M be a 3-connected ternary but non-binary matroid. M is near regular. If M is near regular, then it has exactly 3 dyadic representations. If M is not near regular, then it has at most 1 dyadic representation. So exactly 1 if it has one equal. So the number of orientations of a near regular matroid is 1 or 3, depending on whether you're near regular or not. And near regular or not is governed by whether you have a non-Fano, dual non-Fano, or P8 minor. So just 3 minors give you the threshold for that change. Okay, great. So for GF4 representable matroids, what's the relationship between orientations and golden mean representations? And at first, it appears there's not really much of a relation. So U3, I think this is right. It may be 360. I may be off by 12, but it's something close to this. And basically, you figure out the number of orientations by doing those pseudocircle representations. So U36 has 372 orientations. 12 of them are golden mean. Come from golden mean representations. So there's 12 golden mean representations, 300, well, not that inequivalent golden mean representations give you inequivalent orientations. They do, but I'll show you why that's the case later. So, I mean, it's off by quite a bit here. And then the free spike of rank K bigger than or equal to 4, well, the free spike of rank 4 isn't GF5 representable at all, so it has no golden mean representations for any rank bigger than or equal to 4. The number of orientations, 2 to the K times this number here, the Dedekind number, the kth Dedekind number. And that number is like 2 to the K log K, asymptotic to that. So that's Jacala, she showed that in 2007, and not all of those orientations are real representable either. So suddenly, I mean, orientations of binary and ternary matroids were really constrained, but once you get to GF4, I mean, the lid is blown off completely and the number of orientations just explodes. All right. But there actually is, a nice way to identify those orientations of GF4 representable matroids that do come from golden mean representations. They have a nice characterization, and that's what I want to get to. So let's talk a little bit about partial fields and chain groups. So partial fields are introduced by Semple and Whittle. So after Whittle did those results for GF3 representable matroids, him and Charles Semple, they come up with this theory of partial fields. And chain groups are introduced by Tutt, I'm not exactly sure when, as a way of representing matroids other than matrices. So that predates the homotopy theorem, I believe, or maybe it started with the homotopy theorem. I'm not exactly sure. But an updated development of both of these things, unified development, was given by Pendabbing and von Swamm in their 2013 paper. It's very good source for all of this material. Very good source. All right. So a partial field is a pair P, where R is a ring and G is a subgroup of the units of R. So that's a ring. That's a subgroup of the units of the ring. With the only stipulation being that -1 is in that group. Okay. And the elements of the partial field, that's the G. So when you say a partial field, the elements of the partial field are the elements of G and 0. You don't consider the other elements of the ring to be elements. And then there's a special type of element called a fundamental element. So P, so an element of G, or an element of the partial field, is fundamental when 1 minus P is also in the partial field. And if P is a fundamental element, then so are its associates, they're called. So P is fundamental, 1 minus P is fundamental, because 1 minus P is P back again. 1 minus 1 over P is, I think it's this one here. That's fundamental as well. This will be fundamental, this is fundamental, that's fundamental. So every fundamental element comes in groups of up to 6, because sometimes they're not all different. So examples. There's the regular partial field. So it's Q adjoined this subgroup 1, -1. Fundamental elements are just 0 and 1. 0 and 1 are always fundamental elements. They're the trivial fundamental elements. The irregular partial field. So the ring is the field QX, and the subgroup of units is generated by -1, X, and 1 minus X. And the fundamental elements are 0 and 1, and the associates of just X by itself. Right? So the associates of X, 1 minus X, 1 over X, 1 over 1 minus X, X minus 1 over X, and X over X minus 1. So it's got 6 non-trivial fundamental elements. The dyadic partial field, ring Q, and subgroup generated by -1 and 2. Fundamental elements are 0, 1, negative, and the associates of 2. The associates of 2 are 2, -1, and a half. So those 6 associate expressions only give you 3 elements. The golden mean partial field. So here you actually don't have to use Q because G to the -1 is like negative G, something like that. I think that's, well, G bar, right? Anyway, so Z adjoin G, and then the subgroup generated by -1 in G. And the fundamental elements are 0, 1, and then these 6 guys, which are all associates. G minus G, 1 over G, -1 over G, G squared, and 1 over G squared. Then there are these getting a little bit more fancy as far as algebraic structure and partial fields. So there's this nicely named partial field, the Gersonides partial field, and named for the 12th century mathematician, well, 11th, 12th century mathematician and theologian Levi ben Gershon, who studied numbers of the form 2 to the I times 3 to the j, our so-called harmonic numbers. So this Gersonides partial field, the fundamentals are 0, 1, the 3 elements that are associates of 2, and then 6 elements that are associates of 3, 4, and 9. So 9, -8, 1/9, -1/8, -8/9, and -9/8. And you can prove, and then of course you have to prove that those are the fundamental elements, and that involves using Gersonides' theorem. And then there's this one that I discovered, and these are going to be important later. I'll talk about them later. I call it the 5th of pi partial field. So again, the ring is Q adjoin G, and the subgroup of units is generated by -1 G and 2. Fundamental elements are 0, 1, associates of 2. The associates of G, associates of half of G, G to the 3rd and G to the 6th. And I like the name 5th of pi because this fundamental element G over 2 here, that's cosine of pi over 5. And in order to prove that these are the fundamental elements of that partial field, you have to use this result from Carmichael, called Carmichael's theorem, which is a really neat theorem if you want to look it up. I was really shocked the first time I heard it. All right, chain groups. So given an R module, R to the E, so that's formal linear combinations. So E is your basis and formal R linear combinations of E. So given the R module RE, a submodule of that's called a chain group. Elements of the chain group are called chains. And given a chain, an element E, you use C sub E to denote the R value of C at E. And the support of C is all the elements of E where C of E isn't 0. A chain is elementary when its support is minimal non-empty. And then the cool thing is that given C, the set of all minimal supports is the set of circuits of a matrix. Okay, so a chain group is a nice way of representing a matroid, and it's a lot like a matrix. Essentially, it's like the null space of the matrix. Like if you have a matrix that represents a group, or a matroid, the matrix represents a matroid, and you take the null space of that matrix, then that's your chain group. And then the dual chain group is like the orthogonal complement. Now, given a partial field P and C, chain group C in R to the E, a chain is called P primitive when each component of C is in the partial field. And you call C a P chain group when every elementary chain is P primitive, up to scalar multiplication by R. So every elementary chain is P primitive. And this notion of a P chain group is equivalent to the notion of this matrix with special subdeterminants. And that's really the primary contribution of what Vinsoam and Daving did in their 2013 paper, was to take this matrix definition and put it into this chain group setting. Because chain groups, they give you another way of looking at things that's connected to coding theory. You can get rid of partial fields over commutative rings and use non-commutative rings, because talking about determinants of non-commutative rings is opening up a, whole problem you don't really want to deal with, probably. So a p-chain group representation of M is a p-chain group whose underlying matroid is M. And then that's equivalent to the matrix notion. And how do you do minors? Well, if you want to delete an element E from the p-chain group, you just look at the chains whose support doesn't contain E. Now, that's a p-chain group representation of M delete E. And then for contraction, what you do is you take each chain and you puncture it. You take out the coordinate for E. So this is puncturing and shortening from coding theory. They have codes and then they puncture and shorten codes. That's minors and matroids. So C contract E, you puncture the code, you puncture the chain group, and that's a p-chain group representation of M contracted. And then projective equivalence or strong equivalence. So there's two notions of equivalence in matroid representations. There is, equivalence using pivoting and column scaling, and then equivalence using pivoting, column scaling, and automorphisms. Okay, I don't want to use automorphisms, and you'll see why in a moment. So we just use projective equivalence, strong equivalence. We don't use the automorphism at all. Basically, because if you have a golden mean matrix and you look at the oriented matroid that you get from it, if you apply the automorphism of the golden mean partial field, it changes the orientation. So you don't want to do that. So projective equivalence with chain groups, it just corresponds to scaling columns. All right, so for example, here's a golden mean chain group representation of U35 with elements E equal to 1, 2, 3, 4, 5, right there. Right, so I've got one chain in each row of this array here. I've got elements 1, 2, 3, 4, 5, and I've ordered the elements, the columns 1, 2, 3, 4, 5, so that the zeros are on the anti-diagonal here. Given the ordering of the rows is a unique ordering of the columns that gives you the zeros along here for U35. Right? And there's a chain group representation. A couple of observations. So this table only has one chain for each circuit, but scalar multiplication by elements of P preserves P primitivity. Furthermore, elementary chains are unique up to scalar multiplication, because if they weren't, then you could subtract them and make the support smaller, but you're not supposed to be able to do that. They're supposed to be minimal supports. So that's all you need to do, really, to show the chain group, is to just show each elementary chain just one of them. And the rest are all given by scalar multiplication. And then the top rows are just zeros and ones. However, you can always do this up to projective equivalence, because you can scale the columns. And then you can put a -1 here, because -1's always in the partial field. All right. So a Tut flat in a matroid M is a union of circuits. Unfortunately, when Tut wrote his papers on matroid and homotopy theorem back in the 58, he didn't use like this sort of standard notation and terminology that we're used to from Oxley's book. He had his own. And he called a flat, a union of circuits, a flat. Now, what that actually is the complement of a flat in the dual matroid. So I call it a Tut flat. So a Tut flat is a union of circuits, and its dimension is its corank -1. So now you've got this geometric object called the Tut geometry for a matroid. So like for U25, here's the Tut geometry. The points are the circuits, and the lines are the Tut flats of dimension 1. And the whole thing is a plane, Tut flat of dimension 2. So that's U35. Here's Q6. It's got corank 3 again. So the whole thing is a plane. And it is a, you contract this 6 to go from Q6 back to U25. And then you just add in this thing here. and put a 7 on all these other circuits, and then that's the TUT geometry for Q6. So given a TUT flat F and M and a P chain group representation, a circuit tableau is an array where the rows are indexed by the circuits and the columns by elements of F. Well, actually, representatives from the coparallel classes of F. So if L is a TUT line, so a TUT flat of codimension or co-rank of dimension 1, co-rank 2, with 5 circuits, in other words, it's U35. So if L is a TUT line of 5 circuits, then up to row and column scaling, the circuit tableau looks like this, right? Zeros along the anti-diagonal for the ordering of the columns corresponding to the rows. You have ones along the top row, 1 X and Y here, -1 there, and then the expressions in terms of X and Y are here. And what you'll notice from this is in order to be a P chain group representation, 1 minus X and 1 minus Y need to be in the partial field. So those need to be fundamental elements. So in terms of the golden mean partial field, X and Y need to be G, -G, 1 over G, -1 over G, G squared, and 1 over G squared. But what's special about picking 1 over G and 1 over G squared like I did? Well, if you take this circuit tableau and you look at the pattern of signs, you get this, right? You take the patterns of positives and negatives, you get that. If you project it to GF4, you get this. The circuits of a TUT line L have a unique cyclic order, a unique cyclic ordering of the circuits in an orientation so that the tableau looks like that, up to column and row scaling. There's a unique cyclic ordering. So I mean an ordering of the circuits that's invariant under cyclic shifting. So under rotating rows from top to bottom and by reversing the rows as well. So that gives you a unique cyclic order. This GF4 circuit tableau is invariant under cyclic shifting and reversal. So the orientation gives you unique cyclic ordering. The GF4 representation on the circuit tableau here is invariant under those cyclic shifts and reversals. The other possibility for the tableau just switches omega and omega squared. So this canonically ordered tableau for a 5-circuit TUT line in a golden mean chain group representation is unique up to row and column scaling. The orientation gives you unique cyclic ordering so that the orientation is like that. And the GF4 representation looks like this. And of course, the other GF4 representation on the circuit tableau looks like that. So I call this an omega squared tableau and this an omega tableau. But a golden mean chain group representation always gives you this one. Minutes here. So here's the definition. Let M be a 3-connected and non-binary matroid, and let F be one of 2 possible GF4 chain groups representing M. So up to projective equivalence, there's 2 GF4 representations of a 3-connected matroid rather than just 1, because they're related by that automorphism, but we don't want to use that. An orientation O of M is consistently ordered if for every TUT line L of M and M dual, the canonically ordered circuit tableau in F and F dual is this kind rather than that kind. So every time you look at the canonical ordering of the circuits given by the orientation, and then you look at the GF4 tableau, it's this type of tableau rather than that one. So, I mean, various examples. The consistently ordered orientations of U3-6 look like this, right? I mean, which is nice. It gives you that, star, which is, the type of geometric arrangement. It's reminiscent of the golden mean very much. And here's the theorem. Let M be a 3-connected, non-binary, and GF4 representable. If M is near regular, then its 6 golden mean representations correspond 2-to-1 to its 3 orientations. If M is not near regular, then its golden mean representations are in 1-to-1 correspondence with its consistently ordered orientations. So those consistently ordered orientations, those that always give you the same GF4 tableau on the tut lines, those are exactly the orientation, the golden orientations coming from golden mean representations. And how do you prove that? Basically, you have to use the machinery that Tut developed in that first result we talked about before, about totally dyadic or total unimodular representations, this thing called Tut's homotopy theorem. So we go way back to the beginning, and that theorem that he developed way back then, that's still what's going to allow you to prove these results now. And then, okay, so what's next? What about GF5 representable matroids and their orientations? Well, I think they come from either that Gersonides partial field or that 5th of pi partial field. Although we can't really go forward on that yet because we don't have a way of counting orientations computationally. We used Sage computations to do rank 3, but the orientations, we calculated them by hand. So that was a big step. And the problem with U3-6 is that it had 372 orientations, and looking at all of those by hand is not going to be possible. So that's all.
Okay, thank you. So we're going to try clapping. So if everyone can please unmute yourself, and then I'll count to 3, and then we'll all clap. So 1, 2, 3. Okay, and does anyone have any questions? You can just go ahead and ask. Well, my first question was going to be, what about for GF5 representable? And then you stole my question by answering it already.
So like I was saying, there's 372 orientations of U3-6. So I did a calc, and 12 of them come from the GF5 representation, or the golden mean representations, which leaves 360 of them. And there's 360 Gersonide representations of U3-6. So I don't know if they give you 360 orientations, but that would be a really big coincidence, I think, if it didn't.
Do you expect that orientations will just in general arise by kind of coincidence or combinatorial noise, or do you feel that they kind of want to be structured in general?
Oh boy. They're very, wiggly. I mean, there's lots of orientations. The numbers of them are huge. So, I mean, the ones that come from these nice representations have to have something predictable going on in low ranks. Whereas in general, they just don't, because these pseudospheres are just really wiggly.
I was wondering if this sheds any light on the question of real representability. So if you're GF4 representable and orientable, are you real representable?
Oh, no, because the spikes, the free spikes, their orientations are not all real.
No, not the actual representations, but is the matroid representable? If it's so, I know that there are non-realizable orientations, but given a GF4 representable matroid that's orientable, is it real representable? I don't know the answer to that.
I think no. Because the, yeah, then, Oh, so you want a representation that's not necessarily the same as the orientation.
No, not the same. So not a realization.
Okay, all right.
Not a
Yeah.
realization. I just want to know. So for GF, so for GF 2 and 3, that's true.
Right.
And for GF 5 and above, it's false. So, but for GF 4, it's not known as far as I know.
Really? Okay. All right. I'm not aware of this problem. I don't know. I don't see anything off the top of my head that's.
So Rutger showed it wasn't true for GF5 and above, but I think he didn't resolve it for GF4 if I recall correctly.
Okay. I don't know. I don't know if this necessarily has any light to shed on it.
Okay, does anyone else have maybe one more question?
I can't hear you, Shayla.
Oh, sorry. Does anyone else have maybe one more question or anything to add? Okay, I'll end the recording there and then we can have some informal discussion.